Welcome to this short preview of next week's IEST Online Education course, Sine Closed Loop Control. I'm Jennifer Scalina, Communications Associate at IEST, and I'll be the host for today's session. In just a few minutes, I'll be handing the reins over to our instructor, Fred Fay. Thank you for joining us today. This is the third in a webinar series covering 6 essential topics in vibration testing. The program is shown here and also may be found at the IEST website, www.iest.org. Course registrations are available individually for each remaining session. Because this is a short preview, we ask that you please reserve your questions for next week's full presentation. However, you may also address your questions directly to Fred Fay via email after this session. His email address will be provided at the end. IEST also offers classroom training on vibration testing through IEST's Campus Training Series. Please check our website frequently to see when the next session will be scheduled. Custom training is also available. Now, I'm pleased to introduce the instructor for today's preview course on Sine Closed Loop Control, Fred Fay, a member of IEST's senior faculty. Fred has worked in the area of noise and vibration applications for 30 years, including analog and digital control of vibration shaker test systems. He is president of Vibroacoustics Technologies in St. Charles, Illinois, which supplies and supports turnkey vibration test systems. Fred is a senior member and past president of IEST and president of the Chicago chapter. And now, here's your instructor, Fred Fay.
Well, good morning and welcome to our continued series of the different applications in environmental testing. I think we have to remember that these previews and the regular courses are part of a bigger picture, and that is environmental testing of our products. And that is to ensure that our products are designed properly and that will perform in the field the way they were intended. These sessions of sine and random and shock are all referencing these recommended practice DTE 19.1, which is available through the IEST library. It covers a lot of the very important issues of vibration control and selection. And this was made over several years by many of the working group members that are experts in their field and suppliers and broad contributors. When we look at sine testing, it's one of the first real closed loop tests that became available, and swept sine was intended to address the issues of mainly aircraft, turboprop aircraft early on. The other types of tests, random, shock, random on random, mixed mode, different tests, were basically come on after that to simulate different conditions in the field. So we can see, and we look at swept sine, and really this was given to us by our forefathers. You know, they were able to make a sine generator, put it into an audio amplifier and into a shaker that simulates really just a speaker that basically then they could provide tests of swept sine, resonance search, and that generally is the area that we're interested in, that failures mostly occur because of the amplification of a resonance in a structure. And then there's others that we can do, and that is resonance dwell and source dwell. When we look at sine testing, it really comes back to the basics of a sinusoidal wave. And this oscillates between a positive and a negative axis over a function of time. When we look at the actual sinusoid, it has different metrics on it. And these are very important metrics that you need to, when you say you have 1G peak, that it's not misconstrued as 1G RMS, or average, or peak to peak. So it's very important that we look at these, that these metrics are added to our levels. So in reality, when we're trying to simulate a condition in the field on a product, very little of our environment is pure sinusoidal. It rapidly became, with the aircraft wing flutter and modes of failure that really started all of this testing. You know, you can then see that sinusoidal and random are two modes of control that can closely simulate the field. But then, as we've seen in the last 5 to 8 years, some of the new mill standards address this by putting in the actual time waveform. So then that takes from a recording on your product in the field, and that is the best way to simulate your field conditions. So when we look at sinusoidal vibration, we can see that there's D displacement, V velocity, A acceleration, and all at one frequency. But we can see that once we have one unit, displacement, velocity, or acceleration, it is related to each other through whatever frequency you're concerned about or that you're measuring or using. When we look at sinusoidal vibration, we can see that there's different types of sweeps. You can sweep your product to displacement, acceleration, or velocity, and these are typical curves that represent that. When we look at what a real test looks like, we can see that there's some, and this is closed loop now. Now there's many tests that sometimes are open loop, and that means when it's open loop you don't really have a control over the dynamics that are out on top of that shaker head. But you can see that we can close this loop by taking and putting the accelerometer on the product or the shaker, bringing it back into the controller, and having the controller generate these the relationship between input and output, which we call a transfer function, and then we can adjust the output drive to the amplifier to take into account the different dynamics out there in the shaker, and so we can get the target value. So that's the most important part, is this control loop that constantly monitors what's out there, either with one accelerometer or many accelerometers, and then we can make sure that the target drive signal is achieved and maintained. When we look at programming and running a Sine test, it's just not something you want to turn on your computer and go ahead and run a test. There's some values, levels that need to be taken into account. And next week we'll be discussing amplitude compression, frequency compression, and different sweep rates that that are important to consider when you're doing a Sine test. And these are all control parameters, the voltage and the startup and the self-chark, and all these issues will be covered in depth next week. So this would be a sample picture of a test that has multiple accelerometers on it. It's being monitored by many different points, but this shaker here would be in the level of about 12,000 force pounds. And then basically you would run a sinusoidal test example, something like this, and do a crossover frequency at 60 hertz. So you'd run it in displacement, 10 to 60 hertz, 0.011 double amplitude instead of calling it peak to peak. Most displacements are peak to peak and double amplitude because the shaker goes up and down in around a zero axis. And then it also then would run a 2G peak acceleration, 60 to 150. But notice that they're putting in double amplitude and peak, going back to that sinusoidal wave. It's very important, because if you put in 2G RMS or you don't put in anything, there is basically almost there is a 41% difference between peak and RMS. So you can see if you put in the wrong value, you could be 41% off. And then they run a certain sweep rate, in this case, 1 octave per minute. The mill standard calls for generally a 3 octaves per minute, and then a duration. And this is what this test would look like. So you would have, you can see in the table below the graph, you've got the 10 to 60, the reference in inches, constant displacement, and then 2G's peak to go out to 150 hertz. This is what might result from that test on your product. And this is the most important result that somebody is going to want, because you can see that there's 3 main resonances that occur, and those are the frequencies that are going to be the most critical for you to match to the field and test in the lab, and then improve it. Many times people use a computer now. It's a digital system. Back in the analog world, you had to know a little bit more about the tests and all the settings. So now when we go to a computer-based system for the last 25 years or so, many people doubt that the controller or the shaker is actually doing something that they want. So they use these optical wedges, V-scopes, and they're just a small taped triangle. And when the shaker begins to vibrate, you get a kind of an optical illusion. And as it vibrates, it brings back to a crosshair axis of the target vibration. In this case here, it'd be 0.25 inches. And then that way you can verify that the controller has been set up for 0.25, and you can do this at different levels, so you can make sure that you get a visual feedback. In sinusoidal testing, the advantage is that you're at one frequency, and many people want to look for these resonances. And what's really nice about the about sinusoidal testing is that now you can synchronize the stroboscope to the test, and that you can look at these resonances in slow motion, or fixed displacement, and it makes it much easier to first understand what the resonance looks like, and then also to be able to perform some kind of adjustments on your products to improve them, and then verify them by going back into dwell. And this works like this. There's a slip sync, it's called COLA, constant output level adapter, and it basically just offsets the frequency that is coming out of the the controller, so you can look at the device under test in slow motion. Another advantage of Sine is the fact that you can use Sine is used to calibrate accelerometers, but then also in the field you can use different portable devices to use one frequency or multiple frequencies and one amplitude, so you can at least verify, not calibrate in the field, but verify in the field that the accelerometer is performing at one frequency and one amplitude. There's a lot of sources that people have asked me for over the years, and not shown here is the Shock and Vibration Bible handbook. So in addition to that, these are different books and resources that you can use to understand a little bit more about the testing. Okay, that concludes today's preview, and then next week we'll go into depth on a lot of these issues so we can understand it a little bit more. You can see my email address, f_fey@msn.com, and feel free to email me with any questions, or not just on Sine, but any type testing that you might have questions about. So thank you very much, and I hope you can join us next week at the same time. Have a great week.
Thank you. This closes our overview of the education program on Sine closed loop control. If you have any questions, please feel free to email Fred directly at the address shown here. I would like to thank you all again for participating in this course. I hope you will all join us again next week for the full-hour continuing education class on this subject. Details are available at www.iest.org.